So everything that has gone on so far in this afternoon is relevant to what we hope to do in the future. The history of our industry, the presence of legacy wells, and whether or not they are fully sealed, improperly sealed, etc., and the geoscience aspects of in particular, the Cambrian, which is realistically the only repository possible for us here in southwestern Ontario if we are going to sequester industrial scale quantities of carbon dioxide. So I'll talk a little bit about that from the policy point of view, and then move on into some technical aspects of risk that we have to evaluate quantitatively as we move towards possible industrial scale carbon dioxide storage in our thin little basin here in Ontario. What are the policy issues? So basically, here in Ontario, the current Premier promised in 2018 to reduce CO₂ emissions, along with other provinces in Canada. And right now, we are 17 million tons per year of CO₂ emissions short of that 2030 target. And there is no action going on whatsoever to reduce that amount of emissions. The major point source emissions are steel, lime, cement, and petrochemicals. Basically, London area for lime and cement, petrochemicals mainly, but not exclusively, in Nanticoke and Sarnia, then the steel industries, of course. These are hard to abate, these emissions, because they require technological shifts from the current technologies used. And even if we do succeed in that technological shift and eliminate CO₂, we're going to have a period of time where the only way that we can meet emissions targets that our politicians and our society have agreed to is to find some way to sequester some of the carbon dioxide. So the image on the right is essentially what we do in carbon dioxide sequestration. We try to put it into geological strata at depth, appropriate geological strata, and in quantities that are industrially interesting. A minimum for a single project would undoubtedly be in the range of 1 million tons of carbon dioxide per year for a period of 15 years, maybe 20, but at least 15. So that gives you an idea of the scale. So as we transition to new industrial technologies that are carbon light, we find very quickly that this is at least 10 years and more likely almost generational. So right now, Stelco and Dofasco in Canada have been working hard at a pathway towards decarbonization of their steel industry. We know the pathways, but it takes hundreds of millions and billions of dollars to get there. And you don't just throw away a big blast furnace like at Nanticoke, into Lake Erie and build a new one, because the technology has not yet been perfected. We're all convinced that it can be perfected. In fact, the first ton of absolutely carbon-free steel was produced in Sweden about 2 years and a half ago, in the fall of 2023 or 2022. I can't remember. So yes, it can be done. We know how to do it. Time, money, building, perfection, etc. So it's generational in nature. Electric arc furnaces, instead of using carbon, we might use hydrogen, for example, to strip the oxygen out of iron ore and turn it into liquid iron, right? Many pathways. Also, things are coming down the pipeline that we might not be too happy with if we don't decarbonize. The European Union has announced that they will be putting on border adjustment tariffs for products that have significant carbon dioxide emission histories, like cement. Today is a lot of carbon dioxide is emitted in making a kilogram of cement. That is going to be taxed by Europe next year. The year after, the United Kingdom has announced that they will be putting into place border tariffs. If we don't decarbonize, for example, our steel, that means that exports to Europe, the United Kingdom, will be subjected to additional tariffs. So they're coming. Heavy industry in Ontario is largely foreign-owned. These companies have plants in other countries, including the United States, India, even Nigeria in one case, and Europe. Production can be shifted to other plants. If we cannot meet our carbon dioxide emissions, if we cannot reduce the carbon dioxide emission load of products, that is a risk. That's a risk of deindustrialization. So how rapidly has the Ontario provincial government recognized these risks, and how rapidly are they working to address them by perhaps, for example, making carbon dioxide sequestration more easy in terms of getting the right information, understanding a pathway to permits? Unfortunately, the progress is distressingly slow. It is probably impossible to meet our 2030 targets now. 2 years ago, we were wondering whether it might be possible, but now, no. We still have to work this out. So one of the things that's going on right now is the Bill 228. I didn't update this slide, but just yesterday, it was announced that Bill 228 has been retabled in the legislature. The bill died because of the election, the provincial election here that took place a few months ago. We don't know if the bill is going to be given automatic first reading and second reading and then progress, or if it's going to have to start all over again. That process is not known. And there does not seem to be any sense of urgency whatsoever on the part of the provincial government to pursue this pathway, which is a bit surprising considering the importance of these heavy industries that I mentioned: steel, cement, lime, petrochemicals. So now you know the policy problems, you know where we are. You might not know it, but Stelco, which I showed a picture of the Stelco operation on the previous slide in Natiko, they basically have put all of this on the shelf. They started working really hard for about 1.5 years, and nothing seemed to be happening in terms of regulatory pathways. So they can no longer take the fiscal risk. So they spent maybe $20–30 million, and now that the investment is just lying fallow, waiting for a pathway forward in terms of politics and policy. So now I'm going to focus on things that I'm more familiar with. I'm not that familiar with politics, but I do work in the technical area, and I'm going to outline the technical challenges that we have and the risks that we are trying to manage. Remember that our little sedimentary basin here is very small, actually, compared to the basin in Alberta, for example, but our little basin is very close to big carbon dioxide emitters, in Hamilton and Canada Cement and Lafarge and all these kind of operations here that form our industrial base in Ontario. The only option is that nice little wee sliver, that little Cambrian sliver that's important for us. That is the only realistic target for carbon dioxide sequestration in our little basin here in Ontario. Furthermore, it's not really very widely spread. We're going to explain that map in a moment. Essentially, that's an isopac map. The darker the color, the thicker the Cambrian. Well, you'll also notice that in some areas, the Cambrian is entirely absent in that white area in the middle there, just to the east of Sarnia, right? In other areas, it's too thin. 20 meters is not thick enough for an industrial scale injection operation. In other places, it's too shallow. In other places, it's too close to the American border. So that means that we're limited to maybe a fairway that is outlined in that blue map. But it gets worse from a policy point of view, because the current Bill 228 suggests that all of the subsurface rights will be retained by the current owners of those rights. Many of these properties have changed ownership year after year, or they've been passed down to the children, then to the 13 grandchildren, then to the 76 great-grandchildren. And yes, these rights are in the hands of thousands of people. So a project might take 30 by 30 kilometers, one big project, or that's 900 square kilometers. Trust me, there's going to be 50,000 landowners or rights owners. And what percentage of those are going to be necessary to be contacted in order to be able to negotiate with them? Alberta solved this problem in 2008, I believe, by declaring subsurface pore volume that doesn't contain oil and gas or other mineral resources is the property of the state and to be used for the general benefit of society for issues such as waste disposal, say, contaminated water disposal, for example, or carbon dioxide sequestration. We haven't done that in Ontario. It's a risk. Any company that undertakes a project has to deal with that risk. So keep in mind that image. That's what the Cambrian looks like. That is not a picture of the Cambrian, but that's what the Cambrian kind of looks like. It's a ratty, moderate to poor quality potential carbon dioxide repository. This is not a huge, wonderful, thick beach sand. Okay? So I want to outline the risks in not being able to access enough of the pore volume. So we define pore volume in the central block there as all of the volumes between the grains. But then we have to define something else, which is the useful pore volume that can be accessed by injection. For example, simply, you can't inject carbon dioxide into a shale. But you can into sandstones and into limestones as long as the porosity and the permeability are okay. So we have to evaluate how much pore volume we can access in the Cambrian sequence. And by the way, that number is not 10% or 20% of the pore volume. Realistically, that number is 2 or 3 or 4%. And some people might think 4% is being generous. So we are constrained not only by the smallness and the shallowness of our little sedimentary basin, we are also constrained by the fact that the formation is somewhat ratty. So let's look at some of the processes that reduce our ability to access the pore volume. Carbon dioxide injected is extremely low viscosity. It's in what we call a supercritical form, and it has a viscosity that is about 1/100th or 1/50th the viscosity of brine. Your saturated brine in the Cambrian has a viscosity that's about 4 times larger than the viscosity of ordinary water. But the supercritical carbon dioxide is 1/50th of that. So we have this well-known physical phenomenon called viscous fingering, where the very low viscosity injected materials kind of fingers rapidly through the system, and it leaves behind all kinds of pore volume that we will never access. That's lost pore volume. The next mechanism is what we call channeling. This is not dominated by viscosity. This is dominated by permeability. In any sequence, like the Cambrian, we have different sandstone beds of slightly different permeability, maybe only 30% difference, which is quite a small difference. Well, the carbon dioxide will flow in the more permeable zones much more rapidly than in the lower permeability zones. So by the time the carbon dioxide gets to the end of the project, we have a whole bunch of zones that have not been adequately or even touched by the sweeping of the carbon dioxide as we inject it. That means another bunch of pore volume is lost to us. Capillarity. There's a surface tension between the carbon dioxide and the water. And all of you know that, if you put it down very, very carefully, you can actually float a needle on water because of the surface tension. To overcome that surface tension clearly requires a force. And as we push the carbon dioxide in by injection, we're limited in the force, and we can't pop through thin capillary barriers, or in other words, small pore throats. The force that you need is the pressure difference across that interface times the area of the pore throat. Remember, force is equal to, pressure times area, right? That's force. So that means that any pores that are too small will not be breached. And this is just an example trying to show the difference between a coarse-grained material and a fine-grained material. The coarse-grained material may get swept by the CO₂, but not the fine-grained material. Then there's the issue of heterogeneity. On your left-hand side, very homogeneous, we see the effect of the fact that supercritical carbon dioxide is much less dense than water. So when you inject it, it doesn't go out horizontally. It actually tends to be buoyant and go up towards the top of the formation. And all of that stuff where it says SW equals 1 is not accessed by our injection. So that's the buoyancy effect. So far it's been the viscosity effect, the permeability effect, the buoyancy effect, the capillary effect, and of course the heterogeneity, which means sometimes we'll never be able to access some of the pore space because it's surrounded by low permeability rocks, kind of sealed. The final one is distant pressurization. Here, if you look at number 1, just by the well, that's the carbon dioxide zone. Number 2 is the transition. Number 3 is the brine that is being displaced. So you'll see the carbon dioxide zone is very close to the wellbore yet. But on the bottom graph, you'll see that the pressure is very high. But the pressure also goes a great, great distance. Some mathematical modeling done by a colleague of Richard Jackson, my co-author, is looking at things like when the carbon dioxide plume actually gets out about 2 kilometers, the pressure response can be felt easily 30 kilometers away. Of course, that depends upon some assumptions that we're making. And we need better geology and better geological engineering in order to refine those assumptions so that they are correct, or shall we say, less in error, right? And there's always probabilities. I mean, you know, when we say 10 in geology, we don't mean 10. We mean, well, maybe it varies between 8 and 12. That's what we mean, because there's always uncertainty in geology, right? So if I say the porosity is 8%, well, for this little piece of rock, yes. But another little piece of rock just a little ways away, it's 7%. That uncertainty exists all throughout our geological issues. So that means that with this uncertainty, we have to be able to come up with a probability curve, like the blue area that you see there, which will tell the proponent, the project operator, all right, you've got a 50% probability of being able to access 3.3% of the pore space. A 90% probability of being able to access 1.7, and a 10% probability of being able to access 6.8. That gives you kind of a probability domain that allows the client, or the proponent rather, to make financial investment decisions. And those probabilities have to be very, very carefully calculated. That's what we're trying to do in a project I'm working on at Waterloo, right? We have to compare it to other projects like Decatur in the United States, Schleipner in Norway, Aquastor in Saskatchewan, and other projects where data are being collected. Then there's this seismic risk. Back in 1981 to 83, I think, 80 to 83, in Goebel's oil field, which we drove very close to, it's by Princeton here to the east of the 401, there was a water flood. So they jacked up the pressure and they generated earthquakes. 3 of them were actually larger than magnitude 3. When they stopped injecting, the earthquake stopped. Now, that sounds startling. It's not. Anytime you change the temperature or pressure, but particularly the pressure, in the subsurface, you're going to trigger what we call microseismicity, and you may trigger larger seismicity. So in this diagram, I've got those vertical dark bars there at the bottom. These are faults that we know exist in the Precambrian. They are pre-existing faults. We also know that the Precambrian has differential stresses, different stresses in different directions that are quite startlingly different. That means that if we jack up the pressure a little bit, we can trigger seismicity that is large enough to be felt by the local population. That will not be a popular move, for sure. I believe, my colleague Dr. Jackson believes, that the induced seismicity risk and the problem of who owns the pore volume, those two might be difficult enough that the only access to pore volume that we can have is offshore in Lake Erie. And if that's the case, because it's a boundary body of water, bounds to the United States, the federal government must be involved in these issues directly. That's part of our Constitution, is that boundary waters are federally controlled. Long-term temperature impacts. The carbon dioxide will be injected for certain reasons at a temperature of, part of the reason is our climate, at a temperature that's probably less than 10 degrees Celsius. The reservoirs at a kilometer or 1.1 kilometers deep are maybe 35 degrees Celsius, so they were going to cool them by about 30 degrees. Doesn't sound like a lot, but I can do some calculations for you that show you that that actually has a big impact on the stresses in the rock. So large that when you're injecting at a continuous steady pressure, you will move from a stable condition into a condition potentially of hydraulic fracturing that might propagate through the cap rock, losing the integrity of the project, allowing carbon dioxide to escape into the overlying strata. That may or may not be a significant issue because the overlying strata in general are low permeability and porosity, but this must be quantified as well as we can. And now we're looking at the fault reactivation, and here I have suggested a fault in the Paleozoic. But remember that that fault can be sourced down in the Precambrian as well. And because our Cambrian formation sediments touch the Precambrian, pressure increases in our Cambrian will be transmitted very, very effectively into the Precambrian. And if we trigger one of those faults, will it create seismic events that are felt at the surface? It did at Goebels. No guarantees that it will. And if we are injecting offshore in Lake Erie, well, if you're 10 kilometers away from the shoreline, maybe we won't have an issue of felt seismicity. But if a fault does slip, even slipping just a couple of centimeters by a number of small earthquakes, it can impair an injection well. Unfortunately, the pressure and temperature effects are additive. They don't cancel each other out, they actually add together. So where are we? Well, that black streak on the bottom is a 2-lane highway, and it's the roadmap to a project, right? So to clarify the technical framework for an industrial scale operation, I said a minimum of 1 million tons per year, but ideally, if everything works out really well, we hope to be able to sequester 10 million tons per year roughly for maybe 15 to 20 years in our sedimentary basin, helping the steel industries, the lime industries, the cement industries do the transition into low carbon technologies. Because remember, that's virtually generational in terms of time. But what do we need? Well, first of all, I believe that we need to have the pore volume issue clarified by a government that is willing to take the torch instead of just being passive. We have to put into place the right measurements and monitoring and verification standards. We need to have a clear pathway to licensing and liability. None of these are resolved yet. So these are not signposts on the road to a project. These continue to be undefined barriers on the way to a project, and we hope that these barriers are overcome as rapidly as possible. One thing that we need, I assure you, is a public experimental well to address many of these issues quantitatively so we can provide that information to you, the industry, to stakeholders, to proponents of projects, and also to opponents of projects, so that the opposition and the pro forces are based upon science and metrics, not just based on NIMBYism or, don't worry, we'll solve all the problems, the optimism of industry. So in summary, where are we in CO₂ sequestration? We're no closer than we were, or not much closer than we were 5 or 10 years ago. There is no clear path yet. Once a pathway is clarified, we believe that the geoscience and everything will take a minimum of 5 years to get to the point of being able to move forward. So that's 2030, right? These technical risks that I've outlined, we are trying to address some of them quantitatively, and that has to be addressed for each project. And the regulatory agency will have to evaluate that, the oil and gas people in the Ministry of Natural Resources and Forestry. Pore volume access is a risk, as I mentioned. Induced seismicity is a risk, which I mentioned. And long-term repository integrity is a risk, which I mentioned. And all of these must be understood so that we can manage them appropriately, technically, socially, politically, and financially. Thank you.